The modern world has been built on the cheap and plentiful energy provided by fossil fuels. At a time when Western Europe relies more than ever on natural gas, the North Sea bonanza is over and production is on the decline. But the gas men are not sitting idly by. British and Dutch scientists are breaking new ground to squeeze the remaining gas from rock thousands of meters under the seabed.
Keep coming up on the block.
They're building a new generation of state-of-the-art platforms.
Very challenging project.
Pioneering innovative drilling technology.
Okay, let's stabilise there at 25.
And battling the remote and hazardous gas fields of the North Sea.
We stopped the whole operation.
But it will be no easy task.
To me, it's like putting a man on the moon.
These are the new North Sea mega rigs. Two modern superstructures, one Dutch, one British, begin their pioneering journeys into the treacherous North Sea to find one of the most valuable resources on the planet: natural gas. For over 45 years, this precious commodity has been sucked from the rock beneath the sea. The problem is, all the easy-to-find gas has been exploited. Production is on the decline at a time when the UK and Netherlands rely on gas more than any other energy source. Finding new supplies in the North Sea with its turbulent seas and raging gales is a hazardous operation. The solution is an offshore platform, an artificial island that rises from the seabed like a skyscraper.
Installing platforms in the North Sea or anywhere in the world is really, really challenging, but it's just so exciting. It's what gets me out of bed in the morning. It's just absolutely great fun.
During the boom years of the oil and gas industry, size was everything, and platforms were enormous. The Troll offshore gas platform, located off Norway and the North Sea, is the heaviest man-made mobile object ever made, with a weight of 656,000 tons. It stands 369 meters tall. It was made from 245,000 cubic meters of concrete and 100,000 tons of steel, enough to build 15 Eiffel Towers. But the Troll was built during the golden age of North Sea gas, when the gas industry literally had money to burn. Now, some forward-thinking gas companies and men like Steve Kemp are pioneering a new generation of slimline platforms.
Most of the easy-to-get-out gas has already been discovered and produced. So what we're now doing is trying to develop the smaller fields or the more difficult fields. And in order to make those cost-effective, we need to reduce the costs of the platform.
The gas men are gambling on these two platforms to provide the solution. The Dutch-built F3FA is the largest reusable self-installing platform in the world. She's been designed to hoover up the small gas fields that remain. The British-built Ensign platform will be the heart of a technology called fracking that will crack open the ground deep beneath the sea to release gas that has been trapped in solid rock for millions of years. It will take millions of man-hours to build these state-of-the-art multi-million-pound gas platforms, and engineers will have to battle the elements to install them on schedule. It will be a massive challenge. Vlissingen, the Netherlands. A modern superstructure is taking shape. The heaviest self-installing gas platform ever constructed. Most platforms are permanently installed on the seabed. They need to pay for themselves before the well runs dry, and they don't come cheap, so they can only be used on huge reservoirs. John Brusick and his team decided the solution was to build a reusable platform.
That was the key. Design and develop
a platform what is able to install quite easily, and as well make sure that if the reservoir is empty, that you could remove it quite easily from A to B.
The F3FA platform has been specifically designed to detach from the seabed and move to a new gas field. It didn't need to be small either.
It is the largest self-installed platform in the world. And the key thing is that we're able to install the platform to other marginal fields.
It will take 1.5 years to build the F3FA, and the entire project will cost over £200 million. But with its prolonged lifespan, the F3FA should more than pay for itself.
The design life is 20 years, but normally in this part of the industry, you can use the platform probably for almost 30 years, 35 years.
What makes F3FA special is the way in which it is positioned out at sea. After it's floated out on the back of a barge, the legs are lowered down into the sea floor. Then, powerful motors jack up the entire platform above the reach of the waves. When the well is empty, the legs can be pulled up, and the F3FA can be taken to another site. At least that was the plan. The challenge was to transfer the design from the computer screen to the workshop floor. In the vast hangar in Vlissingen, workers are bashing, screwing and welding like the clappers to bring the idea alive. The F3FA platform is built from the bottom up, so the construction began with the cellar deck, where the gas comes on board. Each part of this massive 63-metre by 42-metre frame has to be cut from 4,000 tons of steel plate and welded together to form girders and supports. It looks indestructible, but even superstructures are only as good as the people who build them. And it will take over 1 million man-hours to assemble the 120,000 individual parts. Plonking a steel structure in the middle of the sea would leave it prone to a spot of rusting. So, as each level is completed, it's treated to a lick of anti-corrosion paint. 40,000 litres of paint are needed to protect the steel structure from head to toe. It's not quite the Forth Bridge, but it's one heck of a paint job. The sheer size of the platform has caused the team many sleepless nights.
It's a step change. Some of these platforms have been installed in the past, but they were smaller, around 1,000-ton topsides. Well, this one is in the order of 4,000 tons, so that made it a very challenging project.
When completed, the platform will weigh as much as the Eiffel Tower and be as high as the London Eye. It's so large that the main and mezzanine decks have to be pre-assembled outside the hangar before being craned into position. The completed platform is designed to sit on 4 enormous legs that will need to slide up and down these enormous brackets. Connecting this iron island to the outside world requires a helideck, but by the time it's been craned into position, the once cavernous hangar is full to the brim. This is a massive problem for the construction team. Somehow, they've got to get this 4,000-ton mass of steel out of the hangar so that the 80-metre-long legs can be fitted. Vlissingen, the Netherlands. Workers have completed the first stage of the F3FA offshore gas platform. Now comes the tricky bit. Somehow, they've got to get this 4,000-ton mass of steel out of the hangar so that the 80-metre-long legs can be fitted. In the end, they just wheel it out. It just takes a lot of wheels. 240 of them. This is the self-propelled modular transporter. the ultimate way to carry the world's heaviest loads. Each individual computer-controlled wheel can swivel independently from other wheels to allow the transporter to turn, move sideways, or even spin in place. It's an amazing piece of technology, as long as you're not in a rush. It's incredibly slow, and the platform creeps out of the hangar at barely 1 mile an hour. Two hours later, it's finally in position. The crane that will bring supplies on board can be lifted into place by one of its big brothers. And now the F3FA can finally get the sea legs that will lift it above the waves. Building these 80-meter-long retractable legs involves some epic engineering. Although the concept behind these legs isn't new. Jack-up drilling rigs operate around the world. However, they are designed to be moved on a regular basis and can be brought back to the shore. The F3FA legs needed to be designed to last over 25 years and survive one of the harshest environments in the world. The North Sea, where storm waves can reach 20 meters, wind conditions can rise up to 140 kilometers an hour, and air temperatures can drop to below freezing point. If that wasn't enough, its inaugural position will be close to the Dogger Bank, the location of the largest earthquake ever recorded in the United Kingdom. To cope with these forces, the steel for the 80-meter-long legs needed to be 3 times thicker than normal.
The interesting part was the heavy wall sections we had in the leg sections, which are more than 11-12 centimeters in wall thickness. And these wall thickness were determined based on the fatigue behavior of the structure.
Not only did the legs have to be strong, they also had to be flexible.
Take, for example, a paperclip. If you move that around a couple of times, at one point it will just break. And in fact, that's the same what happens offshore. When a structure is standing there and waves are going through, you will have a constant movement of your structure.
Huge strand jacks with nearly 51 kilometers of steel cable are attached to raise the platform above the sea. When it's up, the platform will simply hang on top.
One of the headaches we had was actually the connection between the legs and the topside. If you look at the construction itself, the whole topside of more than 4,000 tons is only hanging of 16 bolts tightened on the top. That's the way it's hanging, 16 bolts, that's it.
The simplicity of the design enables for a speedy installation and removal. But before the platform can straddle the sea, the legs need to be furnished with some super-sized 800-ton feet. Fitting them is a real challenge. But first, the 133-meter-high structure will have to be carefully loaded onto a barge in the harbour. Hartlepool, the northeast of England. Workers here are building the Ensign platform. It's the latest in a line of compact and economical gas platforms, specifically designed for smaller gas fields. But what the Ensign lacks in size, it makes up for in ingenuity. It takes a crew of 350 to run the monster troll platform. The Ensign doesn't need a single one on board. It's controlled by an electronic brain, the master control station. It's brilliantly efficient, but it's also a computer, and computers can stop working at the most inconvenient moments, so there's always someone keeping an eye on it.
The platform is monitored remotely from a control room. Another platform about 24 miles away. So they can see all the pressures and the temperatures, the positions of all the valves. So effectively, they can operate it remotely. If there are any problems on this particular platform, they can shut it down safely, and they can either restart it from that remote facility, or we can send some people out with a helicopter to land on it and to aid the central facility to restart this platform.
Despite its size, Ensign is a production powerhouse.
When this platform starts producing gas, we should export enough for roughly about 300,000 homes.
But until it's up and running, the Ensign is costing money. The daunting task of completing the build on schedule is in the capable hands of construction manager Andy Close.
The Ensign project started construction in August. By the time we sail away, it will be 11 months. From start to steel, cutting and fabricating, to installing offshore.
He has to turn 550 tons of steel, pipes and electrical cable into a lean, mean, automated gas machine. The engineers are working feverishly to finish. Everything must be in perfect working order before it's transported offshore. Whilst the platform is unmanned, it still needs living quarters for emergency and maintenance work. It's not quite the Ritz, but then it's not a holiday destination. Getting on and off the platform in the middle of the sea is no easy task, so the Ensign is fitted with an aluminium helideck for passengers and a pedestal crane with a 4-ton lift capacity for heavier visitors. In the event of an emergency, the weather can often be too harsh for a helicopter evacuation, so the crew will rely on a lifeboat or the Skyscape evacuation system.
It's basically worked on gravity, with levers inside that you pull automatically. The Skyscape then lowers to the sea. Once it gets to the sea, the pontoon inflates, and thereafter this deploys, and it's a zigzag that we can slide directly down to the pontoon, get into the life rafts without even getting our feet wet, put the rope and paddle away.
Additional safety is provided by a deck-integrated firefighting system.
8 ton of water that's mixed with foam through a piping system that activates like a giant garden sprinkler, putting a blanket of foam on the helideck to extinguish fires.
All of these safety features rest on one thing: the Ensign's sea legs. Towering 50 metres into the sky on the other side of the construction yard is the jacket, a web of pipes that are designed to carry the weight of the Ensign and withstand the power of the North Sea. Calling the shots on this construction is project manager Ken Scott.
It sits in 25 metres of water depth, and in the North Sea everybody knows it's not kind and gentle, and it's not exactly the place to be. Monumental winds, monumental bad seas, and it's got to sustain that strength and that capacity for at least 20 years out there during production.
The Ensign field has its own unique conditions, so the robust jacket had to be custom designed and built from scratch.
Everything originally comes as pieces of steel, girders of various sizes, cans and tubes of various sizes. They are specifically designed to take the lateral loads from high seas and very high winds.
It will take a real battering from Mother Nature, so the jacket must be firmly anchored to the seabed.
In all 4 sections of the bottom of the jacket, we have what we call a mud mat. If you think about it like a camel's foot, it spans out on the sand so that it doesn't sink into the seabed. From then on, a big base foundation, which is the piece that sits on the ocean and is piled in with 50-metre length of piles, which are essentially lumps of pipe driven through a hole like hammering a nail into a wall.
The jacket isn't just the support. it has to protect the gas pipes that will rise out of the sea.
But as you go vertical, as you can see, we rise up through the centre section. We come to the section at the top, which is called the ESDV section of the structure, which is the valves, the shutdown valves, which stops the flow or enables the flow of the process from the seabed. We call it a jacket. It's a bracket, a steel structure mounted on the seabed with a box on the top, which we call a module. It's been a challenge, but I've really enjoyed it.
It's tough building a platform. It's even tougher moving one. The next challenge for Ken and Andy is moving the topside and jacket onto a floating barge and out into the final position in the North Sea. Vlissingen, the Netherlands. The F3FA gas platform has reached the final stage of construction. 4 enormous 800-ton feet have to be added. But first, the 133-metre high structure has to be carefully loaded onto a barge in the harbour. The plan is to roll the platform onto the barge at high tide using modular transporters. However, the F3FA's unique design has made a difficult job that extra bit harder.
The interesting part of the F3 fabrication and transport was the fact that the top side is located 90 degrees on the barge, with the legs hanging on the side, which created a complete different movement during transport.
Loading it will take a precise balancing act. Inside the barge's hull are 17 massive tanks, each containing roughly 10,000 litres of water. At the moment, they're full and the barge is level with the jetty to allow the F3FA to roll on. As the modular transporters inch the F3FA forward, the barge pumps thousands of litres of water out of its ballast tanks. They effectively become metal balloons, keeping the barge afloat and perfectly stable. It's a stressful time for the entire team. One slip and the multi-million-pound superstructure could tip into the harbour. But the boffins have got their calculations spot on. The barge stays steady and the final stage of the platform construction can begin. The 4 huge 5-storey high feet that need to be welded to the base of the legs are in fact suction anchors. Upturned buckets, each big enough to hold more than 2.5 million litres of water. The buckets are designed to sink into the seabed and create a seal.
When you arrive on the field, you lower down the 4 legs in parallel, and due to his own weight, it penetrates already in the seabed approximately between 4 and 5 meters.
A pump then sucks water out through a valve on the top of the bucket, pulling the buckets further into the soil and anchoring the platform to the seabed. It's the final design idea that the engineers hope will make F3FA the largest self-installing platform in the world.
With the suction operation and the bolt connection on the top, you could pick it up from position A to position B in probably 30 days.
The tugs open up their engines and F3FA steams out of the safety of Vlissingen Harbour and heads offshore to retrieve gas buried under one of the most treacherous seas on the planet. Turbulent seas, raging gales and a potentially explosive product make North Sea platforms a hazardous workplace. And tragedies have occurred. In the early hours of July 6, 1988, the Piper Alpha oil rig in the North Sea exploded. 167 men died. The platform was completely destroyed. But lessons have been learnt. At Petrofac Training Centre in Aberdeen, all employees who will operate offshore on platforms like the F3FA and Ensign must complete a thorough safety course.
Although working offshore, if you look at the accident statistics, is a relatively safe industry to be working in, there is a very high hazard content. We're playing with petrochemicals, obviously very dangerous. Very small area that we're working in, the offshore platforms. Although they're big structures, there's an awful lot going on. We've basically built a factory and we've added a block of flats on top, so everything's done in quite a confined space. So the potential is there, so we have to make sure that everyone knows what to do.
The training is a real eye-opener to the potential dangers of the offshore industry, and those who fail won't be able to work.
The point of the training is to give everyone a basic understanding of the offshore environment, all the hazards that go along with that environment. So the training that we give could save lives.
The offshore survival training course begins by introducing each student to the survival suit. During winter in the North Sea, an unprotected swimmer will succumb to hypothermia within minutes. Wearing a survival suit can increase your survival time to hours. But leaping into the sea is a last resort. To save lives, platforms like the F3FA are equipped with state-of-the-art free-fall lifeboats. The biggest of which can hold nearly 100 people and launch from up to 50 meters high. Each lifeboat is designed to survive the most powerful North Sea storms. Getting to and from the platform is also fraught with danger. More than once, helicopters carrying workers to their rigs have had to ditch into the sea. For this reason, everyone must pass the most frightening test of all, the HUET, Helicopter Underwater Escape Training.
The whole point of the helicopter underwater escape training is to prepare anyone for a ditching situation, so from emergency checks to releasing their harness, where their exit points are, so familiarising themselves with the helicopter itself.
A ditched helicopter will usually begin to sink, so with the divers at the ready, the trainees begin the final test. A floating chopper can be extremely unstable. All the weight of the engines are at the top, and one large wave can flip the whole thing upside down in seconds. It's a disorientating and scary test for the trainees. Panic in a real-life situation could be deadly. Success is met with relief and euphoria.
Well, I hope for everyone that comes through here that they never have to use this in a real-life situation, but if they did, they will be prepared for it and they'll know what to do, and it could save many lives.
These workers are ready to venture offshore, and the Ensign platform is ready to be installed. It's a bright summer morning on the docks of Hartlepool in northeast England. And the Ensign platform is finished and ready for transporting. The platform topside has already been safely loaded onto the barge. But the job is only half done. Now they need to load the jacket. It's a worry for the team. The Ensign jacket's height provides a very different challenge to the topside.
It's not just like us lifting a container or a shoebox or something at home or a chair.
The steel tower can be loaded vertically, which will speed up the installation at sea. But its height has made a tricky load-on that extra bit more stressful.
The trickiest time is once it's past its point of no return. We get to a point of where we've committed to going onto the floating pontoon and we can't go back, and I guess that's the most critical time of the exercise. we can't change our mind once it's there.
The front wheels of the loader inch onto the barge. There's no turning back.
It is a critical activity. You'd only need a mechanical breakdown, and then you could get problems as the tide's going out.
Everything goes to plan, and like clockwork, the jacket is fastened onto the deck of the barge. Ensign can finally begin her journey. 4 tugs position themselves around the platform to guide her out to sea. With good weather and calm seas, it should take 2 days for the Ensign platform to rendezvous with the heavy lift vessel Stanislav Yudin at her final destination, 80 kilometers off the coast of Norfolk. But then the hard work really begins. The jacket and topside will have to be craned into position, and for the first time the platform will be exposed to the extreme conditions of the North Sea, and its builders will know whether they have succeeded or failed. After a 36-hour, 150-kilometer journey, 2 tugs pull the Ensign up to its final destination. The task of positioning a gas platform in the North Sea is a daunting one that calls for specialists. The Dutch-operated heavy lift vessel Stanislav Yudin is one of the very few ships capable of such an epic job. It's a floating construction yard designed to lift and install some of the heaviest offshore platforms. At 173 meters long and 36 meters wide, with a deck the size of a football field and a 62-meter crane that could lift the London Eye. Construction manager Andy Close and his boss Chris Bird have flown in to oversee the installation. The unmanned Ensign platform has been designed to process gas from multiple wells on the Ensign field.
The platform has actually got 3 wells, potentially can drill 3 wells into it. So what we've done is drilled 1 well under where the platform's going to go already. So that's already been drilled and completed and tested. And then we're drilling another well at the moment, which is from we call a jack-up drilling rig.
When this well has been completed, the gas will be piped to the platform. They need the Ensign up and running by then. But it's not just a matter of plonking it in the sea. It has to sit precisely over the 1 meter square wellhead on the seabed.
We have a couple of guideposts. So when we put the jacket in that you can see behind me, it will be moved around on the crane, be orientated, and then it'll be slowly dropped to the seabed. Before it hits the seabed, we have a remote operating vehicle with some cameras, and they watch very carefully as we orientate the jacket itself and then drop it down onto the template. To me, it's like putting a man on the moon.
It's a tough operation, but lift specialist Robert van der Ark is itching to start.
We're now on site. We've done all our preparations. The barge has just arrived and we are ready to go.
He has spent months planning this installation using computer simulations.
Do we have sufficient capacity? Do we have sufficient clearances? All that kind of stuff, that's what we do beforehand. And every time the devil is in the detail. So we want to prepare as carefully as we can.
But before any lifting can take place, the Stanislav has to park itself. Andrei Lipnovich is a man who never gets lost. As head of the positioning team, he has to know exactly where they are to the nearest meter.
During the jacket installation, the vessel, it's quite important to position it in the proper way.
Using GPS, he can ensure that the Stanislav is exactly where Robert calculated for the lift. Keeping it there in changeable weather is a whole different challenge. To do this, the ship sinks not 1, but 8 10-ton anchors, each controlled by powerful winches. These winches allow the crew to adjust the position of the ship during the lift and compensate for any drift due to the weather.
When we are down on weather, we have to constantly monitor the anchor's position, just to be aware if the vessel is not being pushed by current and wind to the side, and that means also that our anchors might be dragged on the seabed.
To make life that little bit harder for Andrei, there are hazards on the sea floor.
On this particular occasion, we have one export and one production pipeline on which we have our anchors deployed, so we have to be sure that those pipelines will be saved from anchor wires and anchors itself.
After a few tweaks on the winches, the ship is finally in position. A final meeting of team leaders ensures that every aspect of the lift has been triple-checked.
Installing an offshore platform, there's quite a lot of challenges. And they could be everything from when you actually put the jacket in, the steel structure in, is it going to actually stay on the seabed? Is it going to be stable? Can we get the topsides on? What are the weather conditions like?
Chris Bird can now hand over the operation to lift supervisor Carl Verster. The sky is clear, the sea is calm. It's a perfect day for a platform installation. The mighty crane takes the strain and begins to lift the 750-ton jacket off the barge. All the planning now rests in the hands of the crane operator. Lifting at sea is a delicate and dangerous balancing act. As the jacket is lifted from the barge, its enormous weight causes the ship to list. To compensate, the Stanislav has an enormous 24,000 cubic meters of ballast tanks, specially designed for super heavy lifting. A computerized ballast monitor and control system moves the weight of water around the hull to prevent the ship from capsizing. Ever so slowly, the jacket is swung out over the sea and lowered beneath the waves. Carl takes control. As ROVs scurry around the jacket legs, he directs the crane operator via remote.
Up on the block, Errol. Up on the block, Johan. Up on the block.
A quick correction and a small spin, and the jacket gently sinks towards the sea floor, right on target. As it hits the soft mud below, the feet of the jacket penetrates 3 meters into the sand. Touchdown. It's a huge relief. But as the sun begins to set, there's no time to relax. The first priority is to secure the jacket to the seabed. 4 65-meter-long, 75-ton steel tubes, known as piles, will be hammered through the jacket's feet and into the ground. A crane with hydraulic fingers picks up the piles like they were plastic straws. With the ROV as his underwater eyes, the crane operator swings them into position and lowers them into the open brackets.
Okay, boom down again. Boom down, blocks in.
It's a bit like driving a great big tent peg into the ground and then filling it up with cement to make it rigid, as you would a garden post if you were putting a fence up.
Under the glare of spotlights, the crew beaver away through the night, burying the piles. By daybreak, the last pile is almost finished. But a new day has also brought a new problem. A change in the weather. It's the crew's worst nightmare.
Yeah, we just installed the jacket into the water. Piles have been installed. But at those moments we have to wait. The weather is not what we expected. We cannot work.
Large waves or gusty winds would make it impossible to lift the top side of the platform onto the jacket.
The crane is designed for certain movements. And at the moment the vessel is moving such that we might exceed those limits. So we cannot operate it. When we're lifting, we're having this heavy structure into the crane. And if you want to set it down, you want to do that as nice and easy as possible as you can, because the load will be enormous. Now that we're on weather, the barge is moving a lot. That means that your load will be moving a lot underneath the crane as well. High dynamic loading on your crane might get damaged, but also when you set down the structure, you have a big bang, and that might terminate the project, destroy the structure.
But you by this weather forecast so far, you see the design will give a new weather forecast.
A meeting is quickly called to discuss the impending weather. It's bad news. 3 days of storms are on the way. And Andy makes the difficult call to postpone the installation.
As you can see outside, the weather's closing in rapidly. He had to let the barge go to sail into safe harbour. So that's now heading off to the Humber estuary, where it'll be held till the weather abates and we get a good forecast.
The Ensign platform heads back to port, and the crew are forced to wave goodbye to their schedule. "200 kilometers north of the Netherlands, the F3FA team also have weather on their minds. This severe North Sea environment, with its gale force winds and 15-meter waves, is going to be the F3FA gas platform's home for the next 10 years. She was built to take this punishment.
This platform, you talk about 9,000 ton, engineered and designed for a very harsh environment, close to the Dogger Bank.
But until she's installed, she runs the risk of capsizing. The F3FA had to be loaded onto the barge with the feet hanging in the water. Shipshape, she is not. All eyes are on the weather. If the swell gets above 2 meters, the installation will have to be abandoned. Or worse, she could join a long list of vessels that have met their end in the harsh environment that is the North Sea. Next time on Mega Rigs, it's a race against the weather to install the platforms. The dirty work of drilling begins.
Okay, so got air pickup. 10 seconds to shut down.
And scientists up the pressure to crack open solid rock and release the precious gas.
Shut down pumps.
The modern world has been built on the cheap and plentiful energy provided by fossil fuels. At a time when Western Europe relies more than ever on natural gas, the North Sea bonanza is over and production is on the decline. But the gasmen are not sitting idly by. British and Dutch scientists are breaking new ground to squeeze the remaining gas from rock thousands of meters under the seabed.
Keep coming up on the block.
They're building a new generation of state-of-the-art platforms.
It's a very challenging project.
Pioneering innovative drilling technology.
Okay, let's stabilize there at 25.
And battling the remote and hazardous gas fields of the North Sea.
We stopped the whole operation.
But it will be no easy task.
To me, it's like putting a man on the moon.
These are the new North Sea Mega Rigs. two modern superstructures have begun their pioneering journeys into the treacherous North Sea to find one of the most valuable resources on the planet, natural gas. For over 45 years, rigs have been sucking this precious commodity out of the rock beneath the sea. The problem is, all the easy-to-find gas has been exploited. Production is on the decline at a time when the UK and Netherlands rely on gas more than any other energy source. Finding new supplies in the North Sea with its turbulent seas and raging gales is a hazardous operation. The gasmen are gambling on these two platforms to provide the solution. The Dutch-built F3FA is the largest reusable self-installing platform in the world. She's been designed to hoover up the small gas fields that remain. The British Ensign platform will be the heart of a technology called fracking that will crack open the ground deep beneath the sea to release gas that has been trapped in solid rock for millions of years. It has taken millions of man-hours to build these state-of-the-art multi-million-pound gas platforms. Now, engineers are battling the elements to install them on schedule. The North Sea, 200 kilometers from the Netherlands. A severe environment near the Dogger Bank. It's in this inhospitable location that engineers plan to anchor the F3FA gas platform to the sea floor, 40 meters below the surface.
Slowly approaching.
But this is a gas platform with a difference. She was built to meet a massive challenge. Her mission is to extract gas from small natural gas fields that were previously uneconomical. The solution was to build a reusable platform. John Brusick led the team that built her.
That was the key. Design and develop a platform what is able to install quite easily with the suction pile technology, and as well make sure that if the reservoir is empty, that you could remove it quite easily from A to B.
The brilliance of the design is in its simplicity.
The F3FA platform has been designed to be moved onto location on a barge, and once the barge is on location, the four large legs that it has will drop down into the seabed and will anchor themselves using suction cans. At that point, the rig will be then jacked up into its final position and the barge will sail away.
If they are successful, it will become the largest self-installing platform in the world.
This platform, you talk about 9,000 ton. Engineered and designed for a very harsh environment.
But until she's installed, she runs the risk of capsizing. The platform has 4 enormous feet to anchor her to the seabed. But to get her onto the barge, she had to be loaded on with the feet hanging in the water. All eyes are on the weather. If the swell gets too rough, the installation will have to be abandoned. They've waited 4 weeks for the right forecast, and John is keen to get going.
Fantastisch weer, het is echt heel erg warm. Het is een zomerse dag. Het water is, ja, er zit wel ietsje zwel in, maar dat is niet of nauwelijks.
When the helicopter carrying the installation team arrives, the positioning of the platform can begin. The F3FA will have to spend years being pounded by the North Sea weather, so anchoring the legs firmly to the seabed is imperative. Permanent platforms are often fastened using giant pegs, which are hammered into the ground and then concreted. This wasn't an option for the F3FA. Instead, they decided to use enormous suction cans. Massive upturned buckets, 15 meters in diameter and 13 meters deep, each weighing 410 tons, that will sink into the seabed like a biscuit cutter. Once they're in place, Huge pumps suck the water from within the buckets and the pressure pushes them further into the seabed.
The whole suction operation is that you take out with huge compressors the water and the air, so it penetrates further in the seabed up to 12.5 meters. And then it is fixed in the seabed and ready for lifting the platform.
Not only does this design allow a quick install, the process can also be reversed for a speedy removal. Speedy is a relative term when you're dealing with 4 1,200-ton steel legs. They have to be gently and precisely lowered to the seabed. To do this, they use 12 900-ton strand jacks. A strand jack is a hollow hydraulic cylinder with clamps at each end and a set of steel cables passing through the open center. The jack operates like a caterpillar's walk, with the clamps climbing along the strands. At the speed of 1 meter every 4.5 minutes, the jacks lower the legs down into the water. 3 hours later, the buckets hit the soft mud below. They penetrate 3 meters into the sand, and the pumps are engaged to pull the suction cans further into the seabed. As the sun sets on the second day, the F3FA platform is firmly embedded in its new home. The only problem now is that she still has a 17,000-ton barge firmly attached to her underside. The sea fastenings that kept her steady in transit have to be cut free before she can lift herself up above the waves. The strand jacks crank up a gear and inch the platform upwards, and for the very first time, the F3FA platform is standing on her own 4 feet. When the base of the platform is 10 meters above the waves, the F3FA platform is locked into position, and the barge can slide out from beneath her. The whole process has taken just 2 days and 4 hours, a record time. And for John Brusick, it's the pinnacle of a 40-year career.
This was my last project, and it always been told to quite a lot of people it was the most difficult but most challenging project I ever had. It was a fantastic project.
The F3FA platform stands proudly above the waves, ready for action.
The North Sea is home to some of the most extreme wind and weather conditions you can imagine anywhere, and this installation has been designed to cope with those conditions. So force 10, 11, 12 gales, 15-metre waves are all part of the design and cause this installation no problems at all.
But its mission is far from complete. Next, wells have to be drilled deep into the rock beneath the sea to release those elusive gas reserves. 80 kilometres off the coast of England, the Ensign platform installation has suffered a major setback.
So as you can see, it's quite windy outside here. That's why we stopped the whole operation. We are so-called waiting on weather.
The jacket has been fastened to the seabed, but for the last 3 days it has been doubling up as the world's most expensive bird table. The platform has been sent back to the safety of the harbour. And the Dutch-operated heavy lift vessel, the Stanislav Udin, and her multinational crew remain idle, costing the project hundreds of thousands of pounds a day. It's been a hugely frustrating time for Andy and the team.
East direction across England, Isles.
But at last there is some good news on the horizon. The latest weather report is predicting a small break in the weather.
In reality, we've got this 36-48 weather window to lift our topside in.
They might have just enough time to finish the job. But it's a gamble. Forecasts can be wrong.
So there's not a way back, there's only one go.
The barge will return in just under 24 hours. It's going to be a long night for the crew. Andy doesn't mind though. He's just relieved that the installation is back on track.
The weather's now starting to drop. If it goes to plan, we should be lifting on Thursday afternoon, back on target to be able to complete and get off for the weekend.
Spirits are lifted and the crew work through the night, moving the sea fastening in preparation for the topside installation. The following morning, the work is complete. Right on time, the barge bearing the ensign topside sails into view. Once the barge is moored, a final weather and safety check will decide if the lift can go ahead. It's a tense time for Robert van der Ark.
The moment we lift it off the barge, we try to set it down, is very intense. We've done our preparations, but there may always be snags. Will it actually fit? Will we have sufficient height to put it on the jacket?
Timing is everything. They only have one shot at placing the 450-ton topside on the jacket in a rolling sea.
The moment you try to put it back, there's so much movement, you can never get it in the same position that it once was. And it's not designed to be in any other position. So you have to keep going.
The weather is holding, but they can't afford to delay. The platform will have to be installed at night. The lift is an incredibly precise operation, positioning a massive hunk of steel on a frame with only millimeters to spare. All the while compensating for the rolling sea. 450 tons dangles in the air. With the weight of the platform hanging over his head, a crewman makes sure the topside is perfectly lined up with the jacket. It's less than a meter to touchdown. With pinpoint accuracy, the guide cones slip into the jacket termination points. And then a heart-in-the-mouth moment when, for the first time, the jacket takes the weight. To the untrained eye, it looks like the legs are bending under the weight. But as the experts explain, it's all part of the design.
What was dramatic was the flex that the jacket took. But like all steel structures, it needs to flex. If it doesn't flex, it breaks. So although you could see it rotate from side to side, that basically replicates a heavy storm.
Just over a year after its construction began, the Ensign gas platform stands as a completed structure. It's a proud moment for all involved.
In the end, all's fine. Good job.
Well pleased with everyone involved in it.
By the morning, their work is nearly done. But for the Ensign platform, it's just the beginning. 400 meters north, an operation is underway to drill down into a seam of solid sandstone, kilometers beneath the sea. And to release the gas, engineers will have to conduct the biggest subsea fracking operation the North Sea has ever seen. Knowing where and how deep to drill is in the hands of the geologists. In Aberdeen, on Scotland's northeast coast, geologists are using both high and low-tech methods to hunt down gas deposits in the North Sea. When looking for gas deep beneath the ground, one of the best places to look is the surface. This rocky outcrop on the shore gives geologist Robert Trithel an insight into what's buried kilometres under the North Sea.
So this cliff section behind me is a big thick section of sandstone, and this sandstone got buried down to quite a deep depth, about 3 or 4 kilometres deep. And at that depth, gas gets generated and migrates into sandstone like this, which gets trapped as a reservoir, which we can then drill into and flow the gas out of.
The next challenge facing the geologists was to find these dense sandstone formations deep beneath the sea. To do this, they simply had to listen for them, which may sound strange, but it's exactly what happens in a seismic survey.
Seismic is essentially a way of recording sound waves that penetrate through the earth, and how they reflect back up gives us an idea about variations in the rocks and also whether there are accumulations of gas, oil or water.
Using this technique, geologists identified a seam of tight sandstone 2,400 metres below the Ensign platform. It could contain enough gas for 300,000 homes. But first they need to drill a well, 5 kilometres long, deep into the Earth's crust. And for that, they'll need some heavyweight help. The 15,000-ton jack-up drilling rig, Noble Julie Robertson, is a well-travelled machine. Built in Singapore, she has been drilling wells around the world since the 1980s and helped build the Channel Tunnel. Her latest mission could be one of her toughest. 60 days ago, she was towed into position 400 metres from the Ensign platform under the command of drilling supervisor John Knowles.
The Julie Robertson is a jack-up rig. On each corner there's a leg, and the rig itself can lift up so it floats along as if it was a boat. We lower the legs to seabed, and from that point then the rig actually lifts itself up.
Drilling rigs are self-contained floating factories. Everything on board is designed around a massive drill. Every inch of deck space is crammed with thousands of meters of drill pipe. The crew of up to 98 will live, work, eat and sleep on board, working in shifts to keep the rig operational, 24 hours a day, 7 days a week, until the job is done. And the job is to drill along a narrow seam of sandstone 2,400 metres below the seabed.
So what we want to do is, rather than drilling through it directly, we want to drill along it, like the lead in the pencil. Rather than it being very thin and just drill through it, we want to go down the middle of it.
Drilling this deep and accurately takes an astounding piece of kit. The drill is like a giant domestic drill with an enormously long shaft known as the drill string that is constructed from 9-metre-long lengths of pipe. Towering 50 metres above the rig is the derrick that supports a giant crane known as the top drive. This spins the drill string with its 1,110 horsepower motor up to 260 revolutions a minute and pushes it down through the sea and into the rock. As the drill string is lowered through the drill floor, the next section of pipe is swung into place by the pipe racker. The new length of pipe is screwed into the existing string. Then, under the watchful eye of the driller, the joints are tightened by the iron roughneck. Length after length is added as the drill bit eats into the rock below. It will take approximately 575 lengths to finish the well, and it's back-breaking, dirty work. But the drill team can't afford to be complacent for 1 second. The whole process is fraught with potential danger.
Our main worry is we can get the gas that we're drilling for can come into the well in an uncontrolled manner. It could come all the way to surface. It's got potential for loss of life, loss of the well, environmental issues.
The stakes may be high, but the rewards are even greater. The jack-up drilling rig, Noble Julie Robertson, is drilling a 5,000-metre-long well in the hunt for gas in the North Sea. From the relative comfort of the doghouse, the driller monitors the top drive as it pushes the drill deep into the tough sandstone beneath the seabed.
Okay, Scotty, I'll pick up.
It's a hazardous operation for drilling supervisor John Knowles and his team.
Our main worry is we can get the gas that we're drilling for can come into the well in an uncontrolled manner.
The biggest problem for the drill team is understanding what is happening deep underground.
It's difficult to drill. You know, it's challenging. The well that we are drilling at the moment, the seismics, the geologists predict. You know, they can't tell us exactly what's there. So we have their outline of a well, and we drill to that, but we don't know from minute to minute what is going to come ahead. You know, we could be drilling, and then we could get gas from the formation or water from the formation, or we could lose everything.
The closest thing that the drill team has to eyes and ears are the electronic sensors mounted near the drill bit. It's up to geologists to interpret the data that they send back. The problem is that all this data is for rock that they have already drilled.
And these are all fabulous, and they can tell us lots of things, but unfortunately they're telling us when we're there. You know, it's almost like looking in your mirror when you're driving your car.
For the most part, the drillers have to be cautious, rely on instinct and experience, and work in a very controlled manner.
Everything we do is planned. It's not there's no shooting from the hip.
But even that isn't enough when you're drilling a hole into rock that could be holding high-pressure gas or water.
The main problem while we drill is that all rock below your feet has water in it and gas. And the problem is when you've got it, that wants to come out. So if you drill the hole, just drill the hole in it, it would fill up with water.
High-pressure water or gas blowing out of the well bore is a dangerous prospect. The priority in drilling is to keep the gas where it is until the well is complete. The answer is as clear as mud. A special liquid called mud is continuously pumped down the hole. It acts like a temporary buffer, keeping high-pressure gas or water in the rock formation and out of the well bore.
A specialist on board, the mud man. He's responsible basically to keep the fluid, the mud, at the weight that we require. If we've got too little, we get water and gas coming into the well, which can lead to problems. If we've got too much, we don't drill as fast, and we have the potential of losing our fluid. It is the one thing that we've got that we can control things down there.
The mud also serves a multitude of other jobs. For a start, it cleans the well bore. Drilling grinds up the rock into tea-leaf-sized cuttings, which are brought to the surface by the mud. It also helps analyse the rocks. The mud is passed over a shale shaker to sieve out the cuttings, which are examined by a geologist known as a mud logger, who is constantly on the lookout for oil and gas. The mud also acts as a lubricant and cooling agent for the most valuable component of the drill, the bit.
What you see out here is 3 drill bits that are used. There's an older style bit here, milk tooth bit is what we call it. There's a newer style bit, what we call an insert bit. And there's the newest style bit, what we call a PDC bit.
Just like a domestic drill, picking the right bit is a vital decision. Choose the wrong one and the drilling will slow down, or even worse, the bit can break. When they cost hundreds of thousands of pounds, you don't want to make a bad choice. These tungsten carbide teeth are 3 times tougher than steel, but the drill still has to be checked or replaced at regular intervals. Changing a bit on a drill thousands of meters long is a thankless task. The whole drill string has to be hauled up, dismantled, and then reassembled. It's a worthwhile task, though. This bit has worn down badly. Much more use, and it could have broken down the well. With a new bit in place, the epic drilling mission continues.
The priority for the well is that we get it drilled. It's a success if we drill a hole to 17,000 feet, we've gone through all this, all the equipment, and we haven't hurt anybody.
As each section of the well bore is completed, it's cased with steel pipe and cemented into place to make it safe. 5 days ago, the noble Julie Robertson completed drilling the 5-kilometre-long well into the tight sandstone that geologists believe holds natural gas. But no champagne corks were popped. The work is only half done. The sandstone reservoir won't give up its gas that simply. It's so dense that the rock must first be cracked open to release it. To do this, she'll need some assistance. "250 kilometres southeast of the Ensign platform, the Norwegian-built 3,000-ton Big Orange 18 is steaming into IJmuiden harbour in the Netherlands. She's one of 2 ships that hold the key to the Ensign project's success. Because encased inside the hull of this powerhouse of a ship is the technology to crack open hundreds of metres of solid sandstone and let the precious gas flow out. Wells manager Brian Holland knows that without her, the Ensign project will be a failure.
This whole thing will only be a success if we can actually deliver a gas well.
Splitting rock takes an enormous amount of force. But Mark Norris and his team don't use high explosives. They use a liquid.
Well, hydraulic fracturing is a process where we pump into a well, into the formation at the bottom of a well in very, very high pressures and rates to literally split the rock either side of the well for many hundreds of feet.
Creating rock-breaking pressure requires a tremendous amount of energy. The Big Orange has been designed with that in mind.
The power on board is quite awesome. The whole ship is diesel-electric powered, so it's like a very large power station, providing electricity for all the pumps that are driven by electricity.
6 electric and 3 diesel-power high-pressure pumps deliver 10,000 pounds per square inch, over 30 times more power than a fire hose. But the problem is, once you've cracked open the rock, how do you keep it open?
While that split, or fracture as we call it, is still open, we introduce and pump into it tiny little hard beads. And when we stop pumping, instead of the fracture trying to close, it can't, and it closes on these hard beads. These beads are called proppant, and they prop the fracture open, keeping it open.
Inside these bags are millions of tiny, super tough ceramic ball bearings. They have been specially designed to hold open the rock. The Big Orange has the capacity to carry 725 tons of the stuff. It will take 200 bags to fill the Big Orange's 6 proppant bins, and 6 hours to pump them down into the fracture. These little beads may not look like much, but together they will resist the pressure of kilometres of rock. The load-up is complete. Up on the bridge, the captain sets a course for the Ensign field, and the countdown to fracking begins. It's the final day of fracking for the Ensign project. The Big Orange's partner vessel, the Island Patriot, has arrived with her ammunition of fracking liquid and proppant. As she moors up alongside the noble Julie Robertson, crews jump to their stations and begin hooking up her fracking pipes to the well. These are her weapons, 2 long steel armoured pipes. Each can deliver thousands of gallons of liquid an hour at pressures of up to 15,000 pounds per square inch. The connections have to be triple checked. There can be no errors. Fracking is a complex operation. In the quality control lab, technicians monitor the fluid to make sure the viscosity is just right.
Okay, let's go for the start on LS4.
Final calculations on the exact fracking pressure are rechecked. Too much and the cracks could spread into underground water. Too little and not enough rock will be split.
One of the important things we could really watch out for during our frac design and execution phase is not to propagate the frac down the way into a water leg. That really is the enemy of the fracture business.
Here's where the water is, the water table in the reservoir. We're a little bit concerned this first fracture is getting a little bit close to the water.
Nerves are definitely jangling.
Gareth, go back.
Yeah, go ahead.
Okay, Gareth, go now. Roll over electric pump 1.
Copy that, mate. Electric pump 1 is looking good.
Explosive charges have punched a hole in the well's steel and concrete wall. It's time to get pumping. In the high-tech control centre, the engines are fired up.
Copy that.
Down on the pump room floor, technicians monitor the pistons and pressure. So far, so good. Mark Norris begins the countdown.
Stand clear for lines, we're about to start the frac.
The pumps spring into action and the pressure is slowly increased.
Increase the rate, monitor that pressure. Go ahead and increase to 15 barrels per minute, please.
The fracking has begun. Unlike explosives, it's a slow process.
Fracture doesn't happen instantaneously. It grows in small parts, and it can take 1, 2 or 3 hours to make a very large fracture that's hundreds of feet long and 100 or so feet tall.
Sensors chart the spread of the cracks.
First frac. Stabilise there.
Okay, that's me 25 barrels per minute.
Once the fracture is there and is growing and we're comfortable the process is moving along in a stable fashion, then we start introducing the proppants, these very small, hard ceramic spheres.
After an agonizing few hours, they're done.
10 seconds to shut down.
Five, 4, 3, 2, 1. Shut down pumps.
Okay, pumps shut down.
For 60 minutes. Roger that.
Initial readings indicate that it was the perfect frac, spreading hundreds of meters into the rock.
The frac length's what we were looking for, so that's the one we're planning.
But they won't be sure until the gas begins to flow. First, the well has to be hooked up to the eagerly awaiting Ensign platform. And then onto the Audrey platform, 20 kilometers away. They'll need a lot of pipe. Vigra, the west coast of Norway. It's here on this windswept, isolated island that they build the arteries that transport the gas across the North Sea. This factory is huge. It stretches 3.7 kilometers across the island, covering a total area of nearly 300,000 square meters, making it one of the largest subsea pipe facilities in the world. To lay kilometre-long lengths of steel pipeline in the middle of the sea is a complex engineering challenge, based around a simple household item, the garden hose. Pipelines are assembled at this onshore facility and spooled onto giant reels, mounted onto specially designed ships like the Seven Navica.
Seven Navica was built in 1999. She's 109 meters long, which is just over the length of a professional football pitch. The big reel you see behind me, the main reel, stands 25 meters high, which is about equivalent to a 5-story building.
Surprisingly, the idea behind pipe spooling predates the discovery of North Sea gas.
The concept of reeled pipe was developed originally in World War II for getting fuel across the channel to support the Allied invasion during D-Day.
Long lengths of flexible steel pipe carried part of the 1 million gallons of gas delivered daily from the Isle of Wight to the French coast. The original idea was conceived by British engineers, who also utilized lead piping somewhat similar to a submarine telegraph cable. Following a test operation, cable ships began paying out the pipe soon after D-Day. The pipe, wound on huge drums 30 feet in diameter, was released while being towed across the channel. Near the tip of the Normandy Peninsula,
it's estimated that 173 million gallons of oil were pumped under the channel by Operation Pluto.
the fuel kept our planes, trucks, and tanks operating on the drive on Hitler's Reich.
And now the technology has been modified and perfected to create a web of piping across the North Sea. The first challenge for the engineers at Vigra is creating a 20-kilometre long seamless length of steel pipe. Everything at this facility is on a massive scale. The steel pipes arrive in 12-metre lengths and are stacked on a kilometre-long row of wooden sleepers. They'll need nearly 2,000 of them for the Ensign platform. This fabrication shed has 25 workstations that will mate the pipes together to produce a 1,500-metre length known as a stalk. First, each pipe is lined up. The stalk has to be perfectly straight. When the pipe ends are slotted together, the most important process takes place: the welding. Not only do these joints have to be strong enough to be bent onto the spooling reel, they also have to last for years, buried on the ocean floor. Every weld is ultrasonically tested for imperfections. Only when it has passed can it move on to the next stage. Salt water is highly corrosive to steel. So when the welds have been thoroughly cleaned with a grit blaster, the exposed joints are wrapped with a special epoxy coating to protect them from rusting. After the epoxy has cooled, the surface is sanded to create a smooth finish, before the powered rollers carry the pipeline out of the workshop and onto its 2,000-metre journey to the quay. The reeling onto the ship almost defies belief. The 20 kilometres of 10-inch pipe is wound round the ship's giant reel as if it were cotton, not steel. The guide chute at the back of the ship acts as a tensioner during the reeling to prevent the pipe from buckling. As the pipe bends and deforms around the reel, it's monitored to ensure that it isn't overstressed. It will take the Seven Navica just 3 days to lay this pipeline on the North Sea floor.
Once we get it on the seabed, we'll use spool pieces to tie it into the Ensign platform, and then some of the other pipe we laid earlier in this campaign will be used to take that same gas from the Ensign platform to the Audrey platform where it'll be shipped ashore.
For now, the Ensign waits patiently for the gas to flow. ROVs and divers have installed the Christmas tree at the wellhead, a complex system of valves that controls the gas pressure as it comes out of the well. In a few weeks, Ensign will be hooked up to the well and gas production will begin. The gas will journey down the hundreds of thousands of kilometres of pipeline, transporting it from deep beneath the sea to terminals like Barrow on the coast. Here the gas is purified before it's pumped out to power stations and our towns and cities. The men who braved the elements to put her here hope that Ensign will supply the UK with gas for the next 20 years. When her work is done, she'll be broken down and recycled, maybe helping to build the next generation of platforms. 800 kilometres further north, perched above the waves on her steel legs, the F3 FA is already piping gas to the Netherlands.
So the F3FA field is a gas condensate field. We've got approximately 3 BCM, billion cubic metres of gas, and we're producing about 1.5 million cubic metres of gas a day. That's enough to fire approximately 300,000 households with their warmth.
This superstructure almost runs itself.
Unlike many of the older vessels in the North Sea, this installation has been designed to be manned by a minimal crew, so the entire installation is controlled by 8 people. Typically they work 2 weeks on, and then they have 3 weeks at home, and then they return back to the platform again. Our control room on the F3FA is manned 24 hours a day by 2 people, and those people can see every single stage of the process, from the gas coming into the platform to the gas leaving the platform.
The incoming gas travels out of the well up the inside of the leg into the Christmas tree at 50 times more pressure than the air in a champagne bottle. So it's carefully monitored by Heeresma.
When the gas enters the platform, it's roughly at 300 bars. It's then reduced to platform pressure by means of a choke. The platform pressure is 120 bars. Then it's further reduced to 100 bars, which is the shipping pressure to onshore. By means of these 2 screens, we can monitor all the process systems on the platform.
The platform also has its own mini refinery.
So when the gas enters the platform, it's basically dirty and it needs cleaning. The cleaning is 2 stages, taking away the liquids and drying the gas. Drying is needed to take all the water out of the gas so it can be transported through the export line without any further problems.
100 bars of pressure should propel the gas to the mainland, but if the pressure drops, it's given a helping hand from this enormous compressor. When all the gas has been taken, the F3FA's work isn't done. The world's largest self-installing platform will lift up her legs and move to the next gas field. Some people think that North Sea gas is running out, but the hunt for gas will continue.
So I can see within the North Sea, not just the UK, but if you take Norway, across Denmark, Belgium and into Holland, there are sufficient reserves out there in terms of gas to last us for decades to come.
The future of North Sea gas rests upon these multi-million-pound superstructures and the pioneers that build and install them.